of the second period of the course. We have so two speakers this morning. We will start with Petra Granitzer. Petra is a senior scientist at the Institute of Physics of the University of Graz in Austria. And Petra has been very influential in the field of mesoporous silicon to design ferromagnetic materials and many other things, doing composites. And so Petra, please, it's yours.
Well, thank you very much for the introduction and the kind invitation. So in this presentation, I will give an overview of the work, of our work and the equipment we are using. So in general, we work on the fabrication of borosilicon and the deposition of various metals, especially magnetic ones, inside the pores. And the novel magnetic properties of these ferromagnetic semiconducting composites, which arise due to the nanoscopic size of the deposited metal structures, are investigated with respect to magnetic on-chip applications and also in terms of magneto-optics. Okay, so we are located in Graz, which is 100 kilometers south of Vienna, and our institute consists of 3 departments, and we belong to the experimental physics, and the experimental physics is divided into 3 groups, and our group, nanostructured semiconductors and magnetic materials, belongs to the nano-optics group. So this is the outline of the talk. So first I will address the nanostructured silicon templates we are using. It's borosilicon and silicon nanotubes. Then I will give a brief introduction of our vibrating sample magnetometer and its various options. And in a third part, I come to the magnetic characterization of the composite systems. So while we are working on the fabrication of quasi-regular borosilicon and the deposition of various metals inside the pores, mainly we use nickel, cobalt, iron, and alloys of them. And the semiconducting magnetic composite offers specific magnetic properties which strongly depend on the deposition conditions, which means on the shape, the size, and the distribution of the particles inside the pores. A further topic is the growth of iron and platinum within borosilicon and also silicon nanotubes to achieve hard-soft magnetic composites. And a third topic is the filling of microporous silicon with magnetic materials for magneto-optics. So these are typical borosilicon structures we are using. Here the diameter is between 50 and 25 nanometers, and it's produced from a highly endowed silicon wafer. And you can see this, that with decreasing pore diameter, also the regularity of the pore arrangement decreases and the dendritic growth increases. And for magnetic investigations, it's beneficial to use quite regular arranged pore arrangement, and so mainly we use porous structures with average pore diameters of 50 nanometers. So this is a microporous silicon structure produced from moderately p-doped silicon, and it offers a structure size of about 5 nanometer, which is estimated from photoluminescence measurements. And the further approach, is to use silicon nanotubes. They are fabricated at the chemistry department at the TCU Fort Worth. So first, zinc oxide seeds are deposited on a silicon wafer. Then the zinc oxide wires are grown. In the next step, the silicon is deposited on these wires, and in the final step, the zinc oxide is etched away by a gasless etchant. And at the right side, you see some results of these nanotubes, and what you see is that the inner diameter as well as the wall thickness can be tuned very nicely. So now I will give a brief introduction to our vibrating sample magnetometer. It consists of an electromagnet with a maximum field strength of 3.2 Tesla, and the system is water-cooled, which means the electromagnet as well as the power supply, and this enables to perform measurements at room temperature without any cryogenic fluid. And in using the temperature options, we can operate in a very big temperature range from 4.2 Kelvin up to 1273 Kelvin. So here you see these temperature options in detail. The cryo option works with liquid helium or liquid nitrogen, works from 4.2 or 77 up to 400 K. The SSVT option operates from 77 Kelvin up to 950 Kelvin. Cooling works with liquid nitrogen and up to a temperature of 500 K, nitrogen gas is used, and for higher temperatures, argon gas is used. And the oven option works from room temperature up to 1273 Kelvin. And in this case, argon gas is used to keep the sample space free of oxygen. A further option is the vector coil option. And these vector coils enable to measure the magnetic moment simultaneously in X and Y direction of a sample. And this option can be used at room temperature and also together with the SSVT and the cryo option. So to investigate the electric properties of a sample, the magnetic resistance option is used, so we can perform Hall measurements, measure the resistivity and magnetotransport, and this can be done at room temperature and also together with the cryo option and the SSVT. So here you see some examples of measurements performed with the oven option and the SSVT. And the left diagram, you see hysteresis curves of nickel-filled borosilicon measured with the oven option between temperatures of 100 and 400 degrees Celsius. And it shows the decrease of the magnetization with increasing temperatures. And the Curie temperature in this case is around 360 degrees Celsius. So it can be used to figure out the Curie temperature of samples. And at the right side, you see hysteresis curves of borosilicon filled with nickel cobalt. It's performed with the SSVT option in a temperature range between 85 and 950 K. And you see the decrease of the coercivity with increasing temperature, but the Curie temperature is not reached, which indicates a very high cobalt content. Here, these temperature-dependent measurements of a nickel-filled borosilicon sample shows the decrease of the magnetic moment with increase in temperature and indicates a Curie temperature around 360 K. A further very nice option of our instrument is the possibility to perform fork measurements in a reasonable time. Fork measurements are carried out by saturating the sample in a saturation field, then decrease the field to a reversal field, and then the field is swept back to the saturation field again. And this is done several terms in regular field steps so that you get many fork curves. And the fork distribution is the mixed second derivative. And the fork diagram is the 2D or 3D contour plot of the fork distribution. And it can be used to figure out the magnetic interactions between particles within a sample. And here you see an example of such a fork measurements of a cobalt-filled borosilicon sample. Here you see the series of fork curves, and at the right side you see the fork diagram, which shows the dipolar coupling of the particles inside the pores, which shows this elongated distribution along the HU axis. So a key topic of our work is the fabrication of hard-soft magnetic materials to control the magnetic switching behavior. And in this case, it's crucial to use regular arrangements of nanostructures. And it's important to control the hard and the soft magnetic part. So the aim is to deposit iron, platinum, iron nanostructures within quasi-regular arranged borosilicon and silicon nanotubes. So far, the production of permanent nanomagnets has not been realized, but there is a big demand. And one challenge is to produce nanostructures as small as possible, but big enough that the thermal energy does not dominate and overwhelm the magnetic ordering. And so the goal is to fabricate nanomagnets arranged in a three-dimensional array and to achieve an improvement of the energy product, which approximates the predicted one. So the energy product is determined by the coercivity of the hard magnetic phase and the saturation magnetization of the soft magnetic phase. And it is important to control the volume ratio between the hard and the soft phase. So the soft phase should not exceed twice the thickness of the domain wall, of the wall thickness of the hard phase. And so the main challenge is to tune the chemical deposition to reach this precondition. So now a few comments about ferromagnetic behavior. In general, if you look at the ferromagnetic material, it offers a domain structure. And if we reduce the size of the material below a certain size, it becomes single domain. And this is shown here in this diagram. First, it offers a multi-domain behavior. Below a certain size, it becomes single domain, and by further reduction, it behaves super paramagnetic. And this means below a certain size, the remnant magnetization is no longer fixed due to the particle shape or the crystal anisotropy. The ambient thermal energy is large enough to flip the moment between two stable orientations of the magnetization, and the particle behaves like a paramagnetic spin. So below the blocking temperature, the magnetization is stable. The blocking temperature indicates the transition between superparamagnetic behavior and blocked state. So now I will address the growth of iron platinum particles within silicon nanotubes. So the iron platinum formation is performed in a multi-step process. First, the silicon nanotubes are aptis functionalized, then they are soaked in a solution containing platinum chloride and iron nitride. Then the samples are dried, followed by heat treatment, and finally they are washed. So this formation has been done for various ratios of platinum to iron. It has been done for 1:1, 1:3, and 1:6. And here you see an example of a ratio of 1:6. You see the iron platinum particles inside the tubes, and the average size of the particles is 5 nanometers. So this iron platinum has also done within borosilicon, and in this case, the formation is similar. The only thing is that the borosilicon not receive the aptis functionalization. And here you see an TEM image and an SEM image showing the particles inside the pores. And here you see individual particles with an average diameter of 10 nanometers. So this time here coercivity data of various molar ratios for a borosilicon sample, and coercivity does not vary in a broad range. The deviation is about 5%, and this is in both cases the same. So this comparison here shows magnetization measurements of silicon nanotubes filled with iron platinum and borosilicon filled with iron platinum. Borosilicon is the red curve, and you see that the coercivity for the borosilicon composite is much higher than for the silicon nanotube composite. And one reason is the bigger particle size in the black curve, and with cobalt, this is the black curve, and with iron platinum, this is the red curve. And you see that the iron platinum composite offers a higher coercivity than the cobalt composite, and this is due to the more hard magnetic material. So this comparison here shows data from silicon nanotubes and borosilicon filled with iron platinum and filled with cobalt. And what we see is that in both cases, iron platinum always the coercivities for the borosilicon composite are higher than for the silicon nanotube composite. So a further topic we are working on is the metal filling of luminescent borosilicon. With a ferromagnetic metal, it offers specific magnetic properties. And what we want to do is to exploit the localized surface plasmon resonance of the metal structures and an appropriate coupling of the emitter field of the silicon nanostructures with surface plasmons of the metal will increase the luminescence intensity. So on the one hand, the system is of interest to combine optics and magnetism in one material with adjustable optical properties by applied magnetic technology. The composite is porous in terms of electric, especially first the coupling plasmons metal to the electron excitation of the nanostructure silicon in events of a magnetic field on the optical properties. So the silicon emitter to the and of intensity. The spacer between silicon emitter and metal particle in our case is silicon oxide, and the thickness of this spacer is very crucial. So here we have a microporous silicon filled with nickel. The deposition is performed by pulsed electrodeposition in using the soap. And at the right side, you see the corresponding PDX spectrum of this cross section here, showing the nickel content inside the pores. Photoluminescence investigations show a blue shift of the photoluminescence peak with increasing deposition time. And at the right, in the right diagram, you see an increase of the photoluminescence in with increasing metal deposition. So we also looked at the decay times of the samples, and faster decay times can be interpreted by an increase in the radiative lifetime with increasing metal filling. So now we look at the magnetic behavior of these structures. So we performed the field-dependent measurements in two directions with an applied field perpendicular and parallel to the surface. And what we see that there is a magnetic anisotropy between these two magnetization directions. And what we also see is that the EC axis is for an applied field parallel to the surface. So looking at the activity, the coercivity increases with increasing deposition time due to more interconnections between the metal structures, and also the magnetic anisotropy increases with increasing metal filling. So the same measurements have been done for cobalt-filled borosilicon. You also see the magnetic anisotropy between EC and hard axis magnetization. And you also see that this magnetic anisotropy is even more pronounced than for nickel samples. So about the magnetic behavior of microporous silicon is that the coercivity as well as the magnetic anisotropy depend on the filling time due to more or less interconnections of the metal deposits. The coercivity decreases with less interconnections and approximates to a superparamagnetic behavior. In the case of nickel, the coercivity decreases from about 450 Ørsted for a filling time of 50 minutes to about 150 Ørsted for a filling time of 5 minutes. And in the case of cobalt, the magnetic anisotropy between EC axis and hard axis magnetization is even more pronounced than in the case of nickel samples. So for comparison, I show you some results for nickel particles deposited within mesoporous silicon. The mesoporous silicon offers a pore diameter of about 50 nanometers, and the pores are oriented and separated. The particle size of the nickel is comparable to the particle size of the nickel structures within microborosilicon. So due to their size, they are super paramagnetic, but due to weak magnetic interactions, the system offers a ferromagnetic behavior. We performed the same magnetization measurements with an applied field perpendicular and parallel to the surface. And what we see is that there is a small magnetic anisotropy between these two magnetization directions. And what we also see is that the easy axis in this case is for an applied field perpendicular to the surface, which means parallel to the pores. So what we can say about mesoporocan is that the coercivity as well as the magnetic anisotropy strongly depend on the shape and the size of the metal deposits, as well as on the magnetic interactions between the deposits of adjacent pores. The coercivity decreases with increasing lengths, which means that the coercivity of particles is higher than of wires. The magnetic anisotropy between easy axis and hard axis magnetization increases with increasing distance between the pores due to less magnetic interaction. And in the case of nano-sized nickel particles, the magnetic anisotropy is small between easy axis and hard axis magnetization, and this is due to weak magnetic coupling. So in conclusion, I introduced our vibrating sample magnetometer and its various options. Beside magnetization measurements, also field and temperature dependent transport measurements can be performed. An advantage of the vibrating sample magnetometer is that no liquid nitrogen or helium is necessary for measurements at room temperature and with the oven option. The measurements are very fast, so hysteresis take just a few minutes, and which allows the performance of such fork measurements. And this is in contrast to a squid magnetometer. A squid magnetometer always needs liquid helium, even for measurements at room temperature, and it's very slow. So hysteresis would take many hours, for example, in average 8 hours, and here you need a few minutes. In the case of hard soft magnetic materials, I showed you the deposition of iron platinum particles within nanostructured silicon and the influence on the energy product. And for nickel-filled luminescent borosilicon, I showed the influence on the metal filling on the optical and magnetic properties. The magnetic response shows that the system offers a magnetic easy axis for an applied field parallel to the surface, and this is in contrast to mesoporous silicon. So these are the group members and our collaboration partners, and thank you for your attention.
Thank you very much, Petra, for this very nice presentation and overview of your activity in your laboratory. It's always very interesting to have a bit of background of what people in this community can do, and it's very interesting. We have time for a few questions, please. Okay, so maybe I would start with one or two questions, Petra. I was curious in the case of the filling with the soft hard material with it was before with the nanoparticles, with the iron platinum nanoparticles. You did both, you did the nanotubes and the nanoparticles of borosilicon, right? And in the case of the nanotube, you have used APTES, aminopropyl trihydroxysilane, before soaking the material to immobilize the nanoparticles.
Yes.
And I was wondering why you didn't use APTES in the case of the porous silicon particles, while you use it for the nanotubes.
The particle deposition has been performed at the TCU, so actually I'm not quite sure why.
Okay.
I think it just didn't work with the APTES functionalization, but I can't say the reason why.
Okay. And a second question is more about the relation that you have shown on the magnetization measurement. It was in the case of the same case, the porous silicon nanoparticles with iron, platinum, and then apparently it's much higher for what I understood with the nanotubes, no, with the particles than with the nanotubes. And I was wondering which parameter you can eventually adjust in the nanoparticles texture to keep increasing these results.
Oh, I think the coercivity is higher in the case of the borosilicon because the particle size of the iron platinum is higher. So it's around 10 nanometers, and in the case of silicon nanotubes, we have an average size of 5 nanometers, and so they are super paramagnetic, and the filling is, I think, less in the case of the tube, so there are less particles, they do not magnetically interact. And in the case of the borosilicon, if you have more particles and they magnetically interact, they offer a higher coercivity.
Okay, so it's related to
yeah. You have to get more particles inside the tubes, or grow bigger particles inside the tube, so to increase the coercivity.
All right, I get it. So it's more related to the number of particles rather than the size of the particles. You think or the amount of material?
Yes. On the one hand, the size of the particles, and also the amount. So if they are close together and magnetically interact.
Okay. Thank you very much, Petra. Do we have other questions for Petra now? I don't see any raised hand. All right. So Petra, thank you very much again for the very nice talk you gave and for accepting to participate to this webinar. It was very interesting, always, and always to hear what you're doing. So now we can move to the next talk. And the next talk will be presented by Nataša Novak. Nataša is a full professor at the University of Nova Gorica in Slovenia. And today she will be presenting her activity about the titanium silica porous photocatalyst, and in the particular case of pollution remediation. Nataša, it's your time. If you can load your presentation. Maybe.
Yes, hello. Maybe the previous speaker has to remove the...
Yes, yeah. Maybe Petra, if you can stop sharing your screen. Thank you.
Okay.
And
okay.
Nataša, the screen is yours.
Yes. Do you see?
Yes.
Okay, but I don't see now. I'm sorry. Okay. Now you see?
Yes.
Okay, good. how can I say, good morning still, no? Ladies and gentlemen, dear colleagues. So thank you very much for the short introduction and also the possibility that I present our work here at this webinar for the cost action. So I'm coming from the National Institute of Chemistry and University of Nova Gorica from Slovenia. And today I will share with you a part of the research we are working on. So maybe first for just for a short introduction. So Slovenia, as you see, is actually very in the middle of Europe, and our institute is located in Ljubljana. This is the capital of Slovenia, and I would like to share with you the information that Ljubljana was European Green City in 2016. So welcome to visit Ljubljana. Our institute is located almost in the center of Ljubljana, and we have more than 70 years of tradition. In 2013, Pregel Research Center was built, and from 2013 we have very sophisticated equipment. So this is the Pregel Research Center. This is also the building of the National Institute of Chemistry. So the sophisticated equipment in terms of electronic microscopy, nuclear magnetic resonance, and also the high performance of computing clusters. So our research is going into directions, material science and life science, and of course I'm coming from material science. So at the institute we have 9 departments. Our department is Department of Inorganic Chemistry and Technology, which is divided in 2 laboratories, laboratory for adsorbents and laboratory for catalysts. So I'm the head of the laboratory for catalysts. And the basis of our research is that we design and develop porous materials for different applications in adsorption and catalysis. So the materials are oxide-based materials, then some specific materials like zeolites, metal organic frameworks, and so on. And of course, we are working in all steps needed for the development and the design of these materials, from the synthesis to characterization, calculation, testing, and scaling up. So our applications are heat storage, gas separation, storage conversion, drug delivery, air and water purification, and also hydrocarbon conversion into valuable chemicals and fuels. So I will talk today about the materials for energy and environmental applications, or mainly environmental applications for air and water purification. And actually, these are materials, they are very, very hot topic nowadays, also for other applications. But before I go to the scientific part, I would also like to share with you the doctoral study materials. So I am the director of doctoral study materials at the University of Nova Gorica, which is located close to the Italian border, close to Trieste. And this doctoral study is actually the combination of research at the National Institute of Chemistry and University of Nova Gorica, and is very interdisciplinary. So we have here the combined expertise of knowledge in physics, chemistry, and chemical engineering. So if you are interested in this, please go to the website here and you can read more about this program. So now I go to the scientific topic. Titania silica porous photocatalyst for pollution remediation, and I will focus first to the air cleaning. So as you all know, volatile organic compounds are one of the major pollutants in indoor air, and the sources are transportation, consumer products, and industry. And what is very dangerous, a long-term exposure to VOCs causes sick building syndrome. So this is very dangerous disease for the people in the buildings. And that's why we need to improve the air quality. Of course, if we want to improve the indoor air quality, then we have to control the source so that also outdoor air quality will be okay. Then we can increase ventilation, but this is not very good option because sometimes we can import more VOCs from outside air to the indoor environment. So it seems to be air cleaning the most feasible option. And for air cleaning, of course, we have different air cleaning technologies. And at Syracuse University in United States, one study was recently concluded on different indoor air cleaning technologies. And as you see in this figure, we have very different technologies, so air filters, photocatalytic oxidation, ozone oxidation, air ionization, botanical treatment. And it seems to be the photocatalytic oxidation, the key technology for air cleaning. Air filters are very popular, but they are actually only they only absorb VOCs. And we still then have a waste, no? So that's why we would like to destroy our pollutants in air, so that we can do with photocatalytic oxidation. Of course, very, I would say, environmentally friendly would be botanical treatment. So that means that we have in our rooms, in the buildings, plants which use volatile organic compounds as food. So that would be the most, I think, effective solution. But if we want to clean the air, as I said, the photocatalytic oxidation is the key technology. And all this air cleaning technology were tested on different VOCs. Here we have 4 of them, which typified physical properties of different groups of VOCs in the indoor air. So if we look at just a figure or a scheme of the air cleaning device in our rooms, we can see that we have several different built-in filters inside the device. So this is one of the cleaning devices you can find everywhere. And we have different filters, and one of the filters could be titania filter. So that means that we have some kind of carrier for titania coating, honeycomb carrier, and titania coating on this filter. So this is the basis. Here I put in on the slide the mechanism of photocatalytic oxidation. I will not go in the details because this is the well-known mechanism, and also the cost section is dedicated for such a materials, so semiconductors. So maybe I can just emphasize the most important characteristic. So we need to have appropriate band gap, and we need to have appropriate adsorption for further surface reactions on the surface of our semiconductor. Titania properties like light absorption, charge transfer, and surface adsorption, they are all closely related to defects disorder, which is the most important defects disorder are oxygen vacancies, and this plays a significant role in the photocatalytic performance of titania. But titania has some limitations, and these limitations are low surface area, low quantum efficiency, and low affinity towards hydrophobic compounds. Also, the absorption of UV light only is one of the limitations, but for air cleaning, we usually use in the air cleaning devices UV light only. So in this case, this is not the limitation. So if we want to improve all these limitations, except the absorption of UV light only, we can add to the titania silica. So why silica? Because of its high surface area, hydrophobic character, the possibility of formation of silicon oxygen titania cross-linking bonds, and then that means oxygen vacancies in titania, high adsorption, and it's transparent to UV radiation. There is also the short introduction to porous silicates. So the well-known are zeolite structures, which are well-known already 18 years, and they are used in as catalysts in oil industry. They are porous aluminosilicates, crystalline, with pore sizes up to 2 nanometers. So they are microporous silicates, and this is also their limitation. So in early 90s, mesoporous silicates were discovered with ordered and disordered structure. So from ordered structures, the well-known is SBI15 with hexagonal arrangement. Then we have also some known structures with layered and cubic arrangements. And of course, we know very well disordered structures. Carboxyl is one of the well-known at the market. And in our laboratory, we synthesize KIL structure, which is also one of the disordered mesoporous silica with pores from 2 to 50 nanometers. If we look at the state of the art of the titania silica photocatalysts, we see that we have at the market titania powders in different, we have different products at the market. For example, P25 is well known, and they are usually synthesized via salt gel synthesis. But also titania colloidal solutions are available. They are prepared in a little bit different way with different chemical precipitation and peptization processes at low temperature from different precursors. And one of them is the precursor is metatitanic acid. So we were involved in the collaboration with Cincarna company, which is titania producer in Slovenia, and they produces titania colloidal solution from precursor metatitanic acid. So we have also several silica supports available on the market. So zeolites, disordered mesoporous silica, and also ordered mesoporous silica, as I mentioned, SBI15 and also colloidal silica. I would like to point out on the very nice review from 2015 in ChemRev from Sylvia Gross concerning silica supports. And of course, we have available on the market several carriers, which are important for the deposition of coatings, which could be honeycomb monolites from ceramic, from different metals. Very popular is aluminum, and also glass carriers. So if you want to use titania or titania silica composites for air cleaning in air cleaning devices for indoor airs, of course we need to have coatings, and this coatings have to be deposited on the carriers. So between 2002 and 2006 there were highly cited studies published in titania SBI15 composites. And we studied all this published literature, and we discovered that actually there were some kind of incorporation of titania nanoparticles into different porous silica. And we started to work on this more than 10 years ago, because we wanted to actually combine titania and silica, so not to have only incorporation of, I don't know, 10% of titania into the silica. And our first study was in 2010. We combined titania, powdered titania, and powdered porous silica. We combined SBI15, we combined also disordered silica, as I mentioned before, KIL, and we discovered that the best performance can happen if we have the molar ratio titanium and silicon 1:1. So we combined also later colloidal titania and powder silica, and now recently colloidal titania and colloidal silica. Mainly when we made a different films, so different coatings on silica, on glass carriers. We use glass carriers and also aluminum carriers. We discovered that the mechanical stability of the films is very poor. So we wanted to have better mechanical stability. That's why we go to the research strategy for improve of this mechanical stability. So as I told you, we prepare titania silica films on glass carriers from colloidal titania and from mesoporous and colloidal silica. Of course, the whole strategy usually is like this, that first we are working on the synthesis part, and then we use very basic structural characterization with different characterization methods. Then we test the catalyst in the photoreactor. In this case, we used two typical model pollutants, which are toluene and formaldehyde. Then we test the mechanical stability of the films, and we comparing the pure titania, so some commercial available titania samples with titania silica composite films. And at the end, we also use some electronic microscopy, so atomic resolution, titania electron microscopy, and X-ray absorption spectroscopy for characterization of our materials. So if we look at the synthesis part, So this is the synthesis of SBI15, which I can share with you. It is a well-known procedure published in Science in 1998. And why I share this with you? Because with this procedure, you can actually modify it in very different ways. And in this way, you can modify the thickness of the walls and also the thickness, the pore size of the pores in this material from 5 to 15 nanometers. So it's really nice synthesis, and you can do really a lot of modifications. So we use these materials, and then we use also a colloidal silica, so the synthesis of colloidal silica, which I will not share with you because we still didn't publish this part, but I can share with you the actually very simple wet chemistry when we are doing the composites. So from titania and silica, so we use the colloidal titania, we use or mesoporosilica or colloidal silica, and we mix these materials in molar ratio 1:1 in propanol. And then we use very simple brush deposition on the glass slides. So of course, this is not for the industrial use, but for the laboratory use is very suitable. So we have glass slides. And we deposit this composite with the loading of 1 milligram per square centimeters. And of course, after we do also low temperature treatment at 150 degrees for 1 hour. So this is very simple procedure. So now I will share with you some characteristics of our materials. If you look at the SBI15, you see that we have very big surface area, and also for sizes around 9 nanometers. If we put the colloidal titania, so this is the products from Sincarna company. We use this product, is denoted with AS. So if we introduce this, or if we combine this with SBI15, you see that we have a smaller surface area, and also the pore sizes are actually in 3 sizes. So we discovered after that also SBI15 structure is somehow destroyed, so partly destroyed. So that combination was not very useful, also from the terms of the mechanical stability of the coating. But if we look colloidal titania in comparison with other commercially available titania P25 and PC500, we can see that we have very similar surface area of colloidal titania if we look at PC500, because this one is in anatase form, like colloidal titania, so we have an anatase form. We have very similar surface area, very similar pore size, and also crystal sizes. This is the comparison with the commercial one. But we combine, of course, the colloidal titania with colloidal silica in the synthesis procedure, and we got, as you see here, also very similar surface area, which is quite good if you compare it with the commercial titania, and bimodal pore size distribution, which actually is also very good characteristic, and also crystal sizes are 2 sizes, so 6 and 25 nanometers. So this material actually showed, as we will see later, also very good mechanical stability. So these are structural characterization with electron microscopy. So we see colloidal titania. We defined titania also with electronic diffraction, X-ray diffraction. So we determined the structure of anatase, and we can see here SBI15 and colloidal SBI15 composite. Here also we see the combination with the transmission electron microscopy investigations, and we can see this partial destruction of SBI15 and some titanium nanoparticles in this structure. So we did the test, the catalytic test, in the photocatalytic reactor for two model pollutants, as I said, formaldehyde and toluene. We made this, we built this reactor in the lab. What is important is that we have a holder for 6 glass slides. We use only 1 glass slide in this holder and 2 UV lamps. And we did the photocatalytic test. So we can see now the results. So for the composition of toluene, I will show it here only for toluene. We can see that we have somehow the best decomposition of toluene, and also with formaldehyde. Even I will not show it here because we don't have enough time. For colloidal titania composite, if we compare this catalytic behavior with colloidal titania, colloidal silica, and SBI, you can see that we have here better absorption, but so high absorption is also not good because it can poison our surface, and we cannot have a good catalytic behavior, photocatalytic behavior. That's why with so around 10% absorption, you see here 10 to 15% absorption. This is the absorption point, and this we have an optimal absorption and a very good decomposition. And actually, if we look the comparison of only commercial titania or the combination of other commercial titania with other silica, we can see that this is really the optimal option. And if we look at further for mechanical stability, we can see that we have for the materials, when we have colloidal silica, we have the best mechanical stability. So here we have also P25 with colloidal silica. It's a little bit lower mechanical stability, but with colloidal we have the highest mechanical stability. And that was also the goal we want to achieve. So if we look at the conclusions and further outlook, so what we did up to now, we prepared colloidal titania and colloidal silica coating with optimal efficiency in terms of absorption and degradation for the removal of two representative VOCs, toluene and formaldehyde, and we have the highest mechanical stability. So for the moment, we are studying still fundamental reasons for this. So our second publication concerning this is in preparation. The first one was published in 2016. Then, if we want to share this application for air treatment for bigger air cleaning devices, so like our climates in the big smart buildings, then we need to have industrial partners. So we are seeking for industrial partner for air cleaning devices that we can use our coatings for such air treatment. And we also did the experiments in real conditions in air cleaning devices. So we have also these results. So in continuous flow air cleaning device. So the further outlook is, of course, wastewater treatment, because if we have such a coatings mechanically stable, we can dop them with different metal nanoclusters, which make our titanium silica material useful and active also under visible light. So that means that we can use it for solar light wastewater treatment, and that means that we can use it in such a solar photoreactors. So we need to have composites which are active under solar light, so with visible light, and that we can do with doping of these materials with different methods. So we did already the preliminary study, and it was published in Journal of Materials Chemistry. So please look at these publications. And I would like to also point out our very recent review on solar-driven photocatalytic films in topics in current chemistry. So welcome to look at our publication. Now, at the end, I would like to acknowledge also my colleagues. So first, the Department for Inorganic Chemistry and Technology. So the people, they worked on these topics are here. So Andrea Schuligo is one of the PhD students in the past who worked a lot on this area. Recently joined us also Gregor Jeriau, who works more on plasmonic photocatalysis with titania, but he's also our substitute. So Andras and Gregor are our substitutes in this cost action. And all this work was in combination with Professor Urška Laurentis-Stanger from University of Ljubljana, who is also the management committee member, as me, of this cost action, and in collaboration with the University of Antwerp, Professor Peggy Kuhl, with our bilateral projects of two agencies, Slovenian Research Agencies and Flemish Research Agency, and in collaboration with France, from CNRS, the Mohamed El Roth, from a laboratory from the university in Caen. And with this, I would like to thank you very much for your attention. And if you have any questions, I will be glad to answer them. Thank you.
Thank you very much, Natasha, for this great presentation. It's very interesting. We've moved to new materials and very new application. We can see all the diversity of what people do, and in particular in your institute. And I'm sure you probably have so much more to present. It was very, very interesting. Thanks a lot for presenting your very nice research center. It's always good to see where people are located and the research center. So are there any questions for Natasha now? Any hand raised? So I may have a quick question for you, Natasha. I'm curious about the choice of using porous silica or SBA15. Since you mentioned initially in the beginning the fact that you'd like to have some more hydrophobic substrate to isolate the titanium dioxide. And I was wondering if your silica or titanium was treated somehow chemically, because the silica to me is more hydrophilic, but it seems to work very well. So I was wondering if you have any sort of treatment in your silica.
Yeah, actually, we can play with the silica very much. So this is I think, very nice. We can modify it in different directions. So hydrophilicity and hydrophobicity can be modified in different directions. Yeah. So this is actually, as I told you in the talk, there were really a lot of studies concerning mesoporous and macroporous silica combined with titania, but we wanted to find out what is the origin of the mechanical stability and at the same time a good efficiency, because this was the problem in the past, no? And that is, we are still working now on this. So I think this is the key parameter. We have to somehow we have to have the knowledge about this because of the coatings, if you want to use coatings in the future, you know, for different applications. Yeah.
Okay, so you have a lot of possibilities with silica for sure.
Yes. Yes.
How
Yes.
to modify the surface. It's a very
Yeah.
versatile material.
Yeah.
Great. Any question there? I see people still around. It's almost noon, but okay. So if there is no more question, then I'd like to thank you again, Nataza, and thank Petra again for the nice morning webinar and those two great presentations. Thank you very much for participating to the COST webinar and for giving us this great overview of your work in your laboratories. And we hope to keep in touch in the future through the network.
Thank you very much also for the invitation. Yes.
You're welcome. And I wish you all a very nice day.
Yeah, also me.
Thank you.
Thank you.